all the eigenvalues are positive, and the determinant is positive also. But this is not really going to do us any good in a practical setting for checking if this particular matrix, for whatever second partial derivatives we have, is positive definite. So we need to take these facts and come up with something we can actually use. H is negative definite if and only if minus H, if you negate all the entries, is positive definite. So first, we're going to use this. The fact that the determinant of a symmetric positive definite matrix is positive, because that we can compute. The determinant of H is fxx, fyy, minus fxy squared. So we need to check if it's positive. If it's negative, saddle point. It is neither positive definite or negative definite. It's a saddle point situation if that happens. If equal to 0, then inconclusive. So once you have a second partial derivatives at the critical point, just compute this right away. This will address a couple of cases immediately. If it turns out to be positive, all that's left to determine if that corresponds to a maximum. The reason why this works is the determinant is equal to the product of the eigenvalues. So here, when you only have a 2 by 2 matrix, if the determinant is positive, it means you have two eigenvalues. They have to be the same sign. They're either both positive or both negative. Right, so that's why this works for that. If it's negative, you know, they're opposite sign. So that's indefinite, it's a saddle point. If this is 0, that tells you the matrix is singular and the test is inconclusive. All right. Now, if it's positive, we just need to figure out which one of these cases it is. But the information to do that is on this board already. The diagonal entries. We can just see if they're positive or negative. So if it's positive, then check any of the diagonal entries. Just go ahead and check fxx. If it's positive, then the matrix is positive definite, it's a min. Otherwise, it's going to be a max. So you can ignore all the linear algebra gobbledygook I've been spewing and focus on what's right here. So from a two-variable case, you check the determinant and see if it's a saddle point or conclusive. If it's not one of these, then check if it's positive. You have one more thing to look at. Just look at any of the diagonal elements, and that'll help you differentiate between a maximum and a minimum. So find your critical points where the gradient is 0 or doesn't exist. Then this is your second derivatives test, and then you're done. You sorted out whether these critical points are max, min, saddle point, or if it's inconclusive, then that's kind of like when the second derivative is 0 in the single variable case. You need more information. Maybe looking at a graphical function, maybe looking at how the first partial derivatives behave near that point instead of just at that point where you know they're 0. But I should mention what I've written here. This is for the two-variable case. If you try this in more than two variables, so you go ahead and try computing the determinant, but it's not going to be as informative as it is in two variables because there's too many scenarios based on what the signs that various things can be. So from a determinant alone, it doesn't really tell you as much as in the two-variable case. Don't worry, the problems I've given and also the ones from the book only concern the two-variable case. It's like in the first place.
Okay, relevant.
Yeah. Yeah, and then and certainly what's over there, and yeah, that'll do.
Okay.
Now everything that we've talked about so far concerns a what's called a local maximum or local minimum. So it's not the absolute maximum minimum of a function on the entire domain. It's just where the function is greater than or equal to or less than or equal to values near that point. So you could have a situation like this. All right, here's the absolute maximum, but here are several local maxima and minima. So this approach will find all of those. As long as you can find all the critical points, where the gradient is equal to 0. But in many applications, one is interested in the absolute maximum or minimum. So this is a function we're looking at. So we need to find local min and max. So first thing we need, gradient. So we need partial derivatives of this with respect to x and y, and what would those be? Yep, let's see. With respect to x and, all right, so we need to see where this is equal to 0. So we need 12x plus 4y is equal to 1, because all of these must be 0. We have 4x plus 16y is equal to 3. So now we just need to solve a system of equations, which actually is going to have just one solution. So we can take this equation and rewrite x in terms of y. Then we can take this. So the second equation gives us this. We can take that and plug it in to the second equation. So we get 12, 3 minus 16y over 4 plus 4y is equal to 1. So we have 9 minus 48y plus 4y is equal to 1. What we get is y is equal to 8 over 44, so 2 over 11. And then you can take that value of y and go back to here to figure out x, and x turns out to be 1 over 44. So those are your values x and y that serve as the critical point. What you need to do is see if this corresponds to a max or a min. And for that we need the second partial derivatives. That means we need to take, so here this is fx, this is fy. We need to differentiate both of these with respect to x and y to get our Hessian matrix. Xx, you can differentiate that with respect to x, and what is that going to give us? 12. All right, fxy, 4, and then fyx will also be 4 by symmetry. And finally fyy, 16. All right, so now we just need to see if this is positive definite or not. We compute the determinant of h. So that's 12 times 16 minus 4 squared. So that's 176. So it's positive. So it's either a max, a local max, or a local min. But fxx, 12, so that's positive. Therefore, this is a local min. Here things don't work out nicely because the second derivatives still turn out to be constants. But generally what you'd have to do is they'd be functions of x and y. You'd have to evaluate them at this critical point and then see what you have. This function on a closed interval, AB, so an interval that includes the endpoints, has a max and min. What about the multivariable case? The generalization is that a continuous function on what's called a compact set has an absolute maximum and minimum. And by compact, that means it's bounded. Informally, that means it's contained. You can contain it in a disk. So it's finite in extent. It can't just go up to infinity in any direction. And closed. That means it contains all boundary points. That's the generalization of a closed interval. A closed interval contains its two endpoints. So for example, set x and y such that x squared plus y squared is less than or equal to 4. So this is the disk of radius 2 centered at 0, 0. It's compact because the disk is finite, and all the boundary points, which is the circle of radius 2, those are included in this. Now if I had less than, strictly less than, then this would be an open set. So any set that contains boundary points, and they're defined by inequalities that have less than or equal to, or greater than or equal to, rather than less than or greater than. That's how you can tell if a set is closed, and as long as it's finite in extent, also, then you can say it's compact. So if you have a set like this, a continuous function on a set like this is going to have an absolute maximum or minimum. So what you need to do is, same as before, critical points, then after you take those into account, you have to look along the boundary and see where the max and min are. And unfortunately, whereas here you only have two endpoints to check,